So, okay. Today we are very happy to Tao Xu for our seminar. Tao Xu got his PhD in 2019 from Zhejiang U. It's the same home in institute of our Zhen professor. Yeah. Then he first go to Hebrew University from 2019 to 2022. Then he come to University of Oklahoma since 2022. Yeah. Paul will talk about the PDH. Okay, please.
Thank you very much for the introduction, and thank you for having me here. It's really a fun trip, and we already have a lot of discussions on many interesting physics. And today I'm going to talk about, sorry, is my voice okay? Can you hear me from the back? Okay, thank you. Yeah. So I'm talking about my research works on primordial black holes. And let me first go to the motivations. The way I look at black hole as a particle physics is I always were trying to answer this question: can we use black holes to probe beyond the model of physics? So usually we think black holes are very heavy objects; they are just floating around in the sky, and they are not directly related to beyond some physics. So how can we do that? The possibility is that black holes can be light, and if the black holes are light, the particle production process from black hole can be more active. So we know there are well-known production mechanisms from Hawking radiation and superradiance process. So if a black hole can use its own gravitational potential to produce particles, we can use this to look at beyond thermal particle physics. And there are two possibilities. If this particle production process happened in the early universe, they actually happen, like we don't know if they actually happened, but if they do, it's at the initial stage of the cosmic evolution, and they make the universe as we are living today. And do we need particle production at early universe? The answer is yes. We need to produce particle dark matter, which is theoretically we don't have we don't know what exactly is particle dark matter, and we also need baryogenesis to generate the symmetry of the baryon symmetry of the universe we observe today. And another possibility is that the particle production process is happening at the later universe. So that means there are light black holes around us in the galaxy. They are producing particles very actively. This gives us a chance to observe the black holes that is not coming from the standard astrophysical formation mechanism. The observation of this light black hole itself is an interesting problem. And if these particles, the black holes are producing particles, they can also produce the dark sector particles we are trying to look for. For example, we are looking at dark sector particles with collider experiments. We're looking at the production of dark sector particles from stars, and there's also a chance to produce a dark sector particle from primordial black holes. And let me first start with the black holes we are familiar with. We know black hole exists, and this picture is a black holes that we observe with gravitational signal and electromagnetic signal. And you can see like different blue points means like a black holes. They form a binary and they merge into heavier black holes. Those black holes are astrophysics black holes, and you can see their mass on the left. They are usually heavier than the solar mass, which is quite heavy, 10 to 33 grams. And in principle, can we have like black hole that is light? GR tells it's possible, right? So we know like we have very massive astrophysics black holes from the collapse of stars, and the Chandra cycle limit tells us they have a solar mass. But hypothetically, if we have like overdensity in the early universe, we can form black holes very light. Usually we call them primordial black holes as a PBH in the rest of this talk. And another interesting possibility is that we can generate a lot of overdensity in the current universe with some particle-based models. they will forming very light black hole around us. And this is another interesting that recently people talk about. Why light black holes are interesting? So first, the formation mechanism of primordial black holes need to introduce some non-standard cosmology models. And this is an interesting question of what happened in the early universe. And if the black holes they are heavy they are stable enough, they can become heavy dark matter candidates. And usually for those black holes lighter than us, like the solar mass, the Hawking temperature is higher. Then this is the reason we can have particle production from them. And the black holes have a wide mass range, and we need to look for different possibility of black hole mass with different methods. Analogy of this picture is we will look for particle dark matter. Particle dark matter also have a very wide mass range. We are starting very light wave-like particles whose wavelengths can be compared to the galaxies. And the particle dark matter can be as heavy as an M Planck, as some Planck relic. And this spans more than 40 order of magnitude for the possibility of the dark matter mass. And the black holes can also have a very wide mass range. Usually people think of the lightest black hole mass can be lighter than 1 gram. This is actually the mass of a hummingbird. And they can be as heavy as 10 to 60 solar mass or even heavier if we are trying to explain the existence of supermassive black holes with some primordial origins. Black holes can all, there are all the possibilities here. And in this talk, I will focus on these two mass ranges. The first one is from 0.1 gram to 10 to 9 gram. Those black holes exist in the early universe and evaporate very fast, before 1 second. And they will modify the cosmology. And the other mass range is heavier than 10 to 50 gram. Those mass are about a mass of asteroids, and they are heavy as a huge piece of rock, but their short radius is actually very small, like a proton. Those PBH are heavy enough to be stable today and become dark matter. And I will cover this possibility in the second part of the talk.
And I don't know if you're going to go over there. There's a lot of astrophysical constraints above that asteroid window, and that's why you're not going to cover those. But I don't know if you're going to cover those constraints.
You're right. So it's they can make up a part of dark matter. Their constraint coming from their gravitational interaction if it's really heavy, or their Hawking radiation process. I will go through that a little later. They can be part of dark matter, and there are a window, still a window, but I will see that either later. Yeah.
What size the lower bound on this part of black hole?
It depends on the formation mechanism you assume. So 0.1 gram is like a Planck measurement of the Hubble. I will show it later in the first slide. Yeah, so this is the outline of the talk. I will first go through light PBH mass range in early universe, introduce the black hole formation mechanism and the evaporation of black hole. In particular, I will introduce dark matter model we call recycled dark matter, which is dark matter goes into the black hole and recycle itself to the quark relic abundance. And this is the archive link of the paper we put out. And for the heavy dark matter side, I will talk about the gamma research for the black hole as part of dark matter. And I will introduce the possibility to test axion-like particles with this kind of black hole. And for the heavy asteroid mass range, it's based on work with colliders for axion-like particle and the primordial black hole with Hawking radiation. And if I have enough time, I will briefly introduce our ongoing project primordial black hole superradiance process. So first, let's go to the early universe part. This is the range of light primordial black hole mass. And as I mentioned, the possibilities we assume is from 0.1 gram to 10 to 9 gram. Those black holes are very light. Their lifetime is lighter than 1 second. That means they evaporate before BBN. This is actually the way we determine the 10 to 9 gram as the age of the window. Because if these black holes are evaporating during BBN, there's a huge energy injection of all kinds of stellar model particles, and it will destroy the successful prediction of the BBN we observe today. So by requiring the lifetime of the black hole to be less than 1 second, this leads to an upper limit on the PBH mass of less than 10 to 9 gram. Then how does the low age come? So if we assume the primordial black hole are coming from fluctuation of some density overdensity region. And if we assume around the horizon mass, all the horizon mass goes into a black hole, that means the lightest black hole we can form is coming from the highest temperature we can have after reheating. So the Planck measurement of the largest inflation Hubble parameter is set by this value, and this leads to the smallest PBH mass higher than 0.1 gram. But of course, if we assume different formation mechanism, which is collapsing some sub-horizon mass into a black hole, it's possible to go beyond it. But basically, usually we assume 0.1 gram to 10 to 9 gram is still allowed in the early universe. And if they produce particles, they can modify the cosmology.
And just to be clear, the 10 or 9 limit is from Hawking radiation.
From Hawking radiation, yeah.
To evaporate for 1 second.
Yes, exactly. Yeah. So how does this black hole come from? I'm going to introduce 2 examples from formation mechanisms, but there are actually a lot of different possibilities here. The formation mechanism people usually talk about a lot is the density, the curvature perturbation that's generated by the inflation model. And if we can generate some fluctuations from the ultra slow roll of the inflaton, then we can assume there's a fluctuation as the black curve. So these are the density fluctuation in space. And from the beginning of the cosmic expansion, our horizon is as very small as the red dot here. That means like we're always sitting in part of fluctuations and we don't see the overdensity. So it's kind of like a smooth, and there's no black hole formation because everything is smooth with the horizon. But with the cosmic expansion, the particle horizon expand, and when it's become comparable to the scale of the fluctuation, we see a huge fluctuation within our horizon, and this triggers the collapse to coming from gravity. And you can imagine, because the fluctuation is always at a very large scale, sitting there, waiting for the horizon to expand to the similar length scale. So almost everything within the horizon will collapse into a black hole. And usually we assume this gamma factor to be the fraction of the final PBH mass versus the horizon mass. And like a different kind of calculations on the assumption of the black hole formation mechanism can change this number. But roughly the number is like a 0.2 from the zeroth order estimation. And it's almost like a 20% of mass always go to the black hole. And if we estimate what is the PBH mass coming from as a function of the communicate mode, and the black hole mass can be like a 40 gram, when the communicate mode is 10 to 22 megaparsec inverse. So K is like the inverse of the length scale. When K is very large, that means we go to very, very small scales. For example, our current probe of CMB is 10 to 5 megaparsec inverse. We cannot go to very small scales. So we can only know from our observation of the universe, we don't have large density fluctuations at large scales, but it's possible that we have density fluctuation at small scales and trigger the formation of very light PBH. So for light PBH from 0.1 gram to 10 to 9 gram, so the communicate mode is about 10 to 18 to 10 to 23 megaparsec inverse. So it's still allowed, and it's possible to test them in the future with gravitational waves. But generally, like we have very high temperature formation and at very small scales.
May I ask you about this so-called color type of black holes, with a color charge?
Yes. So I think for those kind of, so do you mean like the black holes is not forming from the curvature perturbation, but the other kind of confinement mechanism?
No. It's still black holes, but with non-zero color charge. I was just listening recently, David Kaiser from MIT, who suggested this type, and I just wonder about your opinion.
I'm not very familiar with the black hole with a color charge. So in principle, you can collapse some asymmetric distribution of a charge. We can have a charged black hole. But for the zero with confinement,
yeah, but they're discussing it at the time which is before QCD transition. So it's much earlier than that. And it's like a Clark-Gluon plasma at that time.
Yeah, so if we here the temperature of forming these black holes is much earlier than the QCD phase transition, and this, I think if we introduce confinements, my guess is like the collapse will not trigger the the gravitational collapse of a whole horizon, and then it will give a different prediction of the final PPH mass we get, because the formation mechanism is very different from the assumptions here.
Yeah. So in this way, I mean, it's up to. I mean, it influences confinement, of course, but when the size is small, then it's also not important, right? I mean, when it's short distances, so it is still there. But no, I'm wondering because it was also about very light, kind of dark matter type of stuff. So that's why I ask. I'm okay. I do not know much about this, but just wonder. Okay.
Yeah. So I don't have like a clear idea to that, but I think like if there's a different formation mechanism given different prediction of PPH mass, it's like interesting. Yeah.
Okay.
Yeah,
Thank you.
So I had a question then on the fluctuations that produce these light black holes.
Yeah.
What's the inflationary potential? How drive?
So for that we need, because the Power spectrum curvature perturbation is inverse proportional to the phi dot of the inflaton. So usually we need slow roll and like a period of like ultra slow roll to enhance the perturbation at a certain K mode, and then go back to slow roll again. And there's some inflation model building like in that part to get the K mode you need for the PPH mass, because K mode and PPH mass are like a one-to-one correspondence. And when the ultra slow happens, and like how long it lasts, like that all goes through the inflation model building part. And there are more details, but
Favorite model?
I'm good with any enhancement of curvature perturbation. Yeah, but mainly for the phenomenology view, like if we can have PPH formation. Yeah, but there are subtleties in ultra slows.
Also, how big do these fluctuations need to be? Do they need to be order 1 or
10 to the negative 2? So like 10 to the negative 2 will generate the fluctuations of your density contrast at like order points few that matches the density contrast for the PPH formation, which are usually at 0.3 or like a third, depends on like the details of calculation. But like 10 to the negative 2 is like roughly the order of magnitude you need the fluctuation to be. Right. Yeah. 10 to the negative 2 is assume the density contrast distribution is Gaussian, and
it's right now. So I guess like you expect a lot of
I think like yeah, certainly like if you get interested in non-Gaussianity, you can do things like at certain locations, and then the prediction of the fluctuation is totally different from Gaussian case. Yeah.
Oh wait, sorry. So you need like the average fluctuations to be 10 to the minus 2, and then you'll have some tail fluctuations which are close to order 1.
Like the density contrast our center at 0, and the variance goes to a larger value, and the tail of the tail goes the density contrast at the tail is higher than the formation threshold, and it gives suppressed formation rates. So basically, you want the variance of this Gaussian distribution to be comparable to the black hole formation threshold, in case like the formation threshold, when you integrate the possibility for the density contrast on the tail, it's not too suppressed.
Okay.
Yeah.
So the variance is like 10 to the minus 2, but I actually need stuff up to like 10 to the minus 1 in order to actually collapse.
I think like the variance is like square root of the curvature perturbation. So if I have like 10 to the negative 2 from P data, you get like a 0.1 from of the variance, then you have like a tail that is not too suppressed. Yeah. Good. So here is the collapse of the horizon mass. And what, like, if we introduce some particle phase model building, we can collapse things that is within the horizon. So suppose we have a first order phase transition from the earlier universe, then like it's like when you're boiling water, so there's a bubbles growing up, and like the surface of bubble is like this blue circle here is the bubble wall, and we assume like there are particles in the fourth vacuum. So these orange dots are particles, and with the phase transition going on, the bubbles will compress. And suppose we have a mechanism to compress all these orange dots within the blue circle, then we generate some local overdensity, and in the end, it will collapse into a black hole. So phase transition is good here because it separates the universe into regions of true vacuum and false vacuum. So you can put things only in one of them. And if we assume the radius of this pocket at the beginning of phase transition is at the order of the horizon size, but they keep like moving particles in a small region to form a black hole, we can estimate what is the PBH mass as a function of a phase transition temperature we want. Again, like to get like order 10 PBH mass as we want, we need the phase transition temperature to be 10 to 15 GeV. So it's a very high temperature phase transition, but you can understand because at that time the horizon size is small, so you can form small PBH. So basically for like the PBH in the mass range we want, we need a phase transition at 10 to 11 GeV to 15 GeV. And when you can trap particles, you can have light PBH formation. And after the PBH formation, we can just describe the behavior of PBH with the thermodynamics. And this is when the Hawking radiation comes in. So Hawking radiation is like a particle production because the gradient of the gravitational potential at the horizon. And you can imagine at the black hole horizon, there are virtual particle pairs. And because the gravitational potential is so strong here, you can have particles, one of them go into the black hole and the other goes out. And to describe this process, we can, the black hole have the Hawking temperature, which is inversely proportional to the black hole mass. So if you put in some numbers here, assume the black hole mass is 1 gram, the Hawking temperature is 10 to 17 GeV. That means if we have a light black holes, they are really good at producing heavy particles that we want. We want like in the beyond star model physics. And the lifetime of the black hole can be also calculated here. Basically, it's proportional to the cube of black hole mass. So the heavier they are, the more stable. And for the light PBH, they have small mass, higher temperature, and faster evaporation. That's what we want for cosmology. And another good part of PBH producing particle from black hole is that it does not care about the coupling. We can form black hole with beyond stellar model particle and the stellar model particle. We put them into a horizon, they form a black hole. But the evaporation part of the black hole does not care about what is coming into the black hole. Like sometimes if there's a charge assigned to a black hole, it will prefer to emit the charge. But generally speaking, the Hawking radiation spectrum is like a black body spectrum. And what only matters is this GF factor, which is the degree of freedom of particle. So as long as we have that particle in the spectrum, it can be produced by the black hole. So
the black holes, they're not spinning, right?
Yeah, we're assuming short black hole. Yeah. Yeah.
Because from this fluctuations, you can't produce any rotating black hole.
Yeah, you're right. So for curvature participation, usually because we are forming the black hole at radiation dominated universe, the curvature, like the density contrast is usually spherical. And for phase transition, we compress like everything to the last stage of the phase transition, and the bubble will have surface tension and make everything spherical. And usually in that case, for black hole formation during radiation dominated universe, we usually assume the spin of black hole is negligible. And there are some calculation on that. I think the average value is 10 to -3 for the effective spin of black hole. So it's really short black hole. Yeah.
Does that represent spin of PBH that depends on how spherical density population you have, right?
Yes, it depends on how you collapse the mass and angular momentum into the black hole. And then for that, you need to really like calculate the evolution of the angular momentum of the density. Yeah, usually you have to do that for matter-dominated universe, or like you already introduce density contrast with larger angular momentum from the beginning, then you can get a spinning black hole.
And maybe you'll get to this later with the spin issue. This is one of the signatures of PDHs is if the black holes we're seeing are PDHs, then they should be very spinless, where it's hard to make those out of star collapse.
Yeah, so yes, you are right. So usually if you assume it's just a spherical collapse during radiation dominated universe, and like the separation between black hole is small, then it's just like a Schwarzschild black hole, like to today. Yeah.
Okay.
People often talk about using early matter domination to get PBHs. Is that just like I don't need that here because I'm already starting with big fluctuations? I only need matter domination if I'm starting with small ones and I need them to grow.
So for if I answer your question correct, so for matter domination, it's easier to generate black hole because like the less of pressure, like and the spin of black hole can be higher. And if we're at really like matter dominated universe, the accretion effect can be stronger, but that depends on what is the mass of black hole. So if it's too light, it tends to lose mass. If it's heavier, then the accretion will make it like a mass increase. Yeah.
Okay. But here you don't need that because you're just already starting with big fluctuations.
Yeah, so here like the what starts the black hole formation is black fluctuations, like before that, not matter domination. Yeah. Okay, so yeah, I'm keep going. So then here is the model of recycled dark matter. It take the second formation mechanism we just see, and if you so this recycling is a new mechanism to form heavy dark matter candidates and through the black hole. So here are 4 steps to make the recycling work. First, we need first of phase transition at a high temperature. The regions in white color are the force vacuum where the value of a scalar field is 0, and the blue region are the true vacuum where the scalar gets a non-zero vector expectation value, and the black and the red dots are like heavy particles that only live in the force vacuum. Then as the phase transition going on, like those particles are trapped only in these force vacuum regions, and the density become higher. In the end, they will collapse into a black hole, and because this black hole evaporates before BBN, they will spit out this dark matter particles again. And if they produce them as a correct radical abundance, then it's a recycle mechanism to put all the dark matter in the black hole and reproduce them as a recycled dark matter.
So here you assume some large coupling or something because the principle these particles can penetrate into the layer 2 bounding line.
Yeah, so I will go through like why we can trap them. Yeah.
And what's the mass of these particles, and is there a limit on their line?
These particles we assume they are stable particle, and the mass of them is determined like by the second step, how we trap them in the force vacuum. If we use kinematics, that means they have to be very heavy to be trapped. So the mass of black hole is actually, mass of dark matter is determined by what the phase transition temperature, and because we want high phase transition temperature for like black hole, the dark matter is even heavier than that. So it's a natural way to explain like why we have super heavy dark matter, because the phase transition is already at high temperature.
It's roughly around 10 to the 11.
Yeah, higher. So like a few tens or like 100 higher than the phase transition temperature. I will show that later.
So the dark matter mass will be determined by the value of the part and
the
coupling. And the rest of the difference between temperature and this value will give the momentum of will become momentum of the dark matter.
If they would,
so when they enter the bubble, they become massive suddenly, right?
When they
enter the bubble, they become massive.
When they enter into the bubble, they become very massive.
Yeah, so they suddenly become massive. Starting from the massless part outside the bubble. When they enter the bubble, they become massive.
Yes, and
so then the difference between temperature and the band.
Yes,
with the coupling that gives us momentum dark matter at the moment.
No, like You're right. So like the temperature controls what is a typical momentum of the particle, and the mass is higher, so they cannot go to the true vacuum and become a heavier particle because energy moment conservation. So they are trapped.
They are going to be bounced back to the
Yes.
bulk
Yeah.
vacuum.
You'll see that again in a few slides.
The wall is gonna expand wise, it helps also to account.
Yeah, that depends on like how like the fluid is really moving in from. Yes, yeah, there are some certain assumptions of that. Yeah. And so this just to show how the mechanism work, we introduce dark sector with scalar particle 5, and it has a potential. It has to it's responsible for the first order phase transition, and then we introduce a fermion chi. It gets a heavy Yukawa mass that depends on the wave. And it can, if the wave is 0, it's massless particle in the force vacuum, and the wave is very large, and it goes to the true vacuum as a super heavy particle. And here we introduce a coupling between star model sector and dark sector. We'll see like how this coupling works in the later. But basically, at a very high temperature, the dark sector and star model sector are in thermal equilibrium. And when the interaction between them become less efficient because the temperature drops, they start to decouple. But usually, if we don't assume some special reheating going on, they roughly at the same temperature until the phase transition occurs. And for the first order phase transition in the field space, here the different curve is the potential of the scalar field. And at high temperature, at the 0th point is the true vacuum. And when the temperature decreases, there's a new vacuum coming up, and there's a turning from the 0 wave to the non-zero wave. And this is the first how phase transition works. And if phase transition happens, the dark particle chi and phi will get a mass. You can think of like Higgs mechanism of the phase transition. Higgs get a mass, the fermions get a Yukawa mass. And if in the special case, when the mass of these dark sector particles is much heavier than the phase transition temperature, so there's a huge mass gap between for them on two sides of the pocket. And this usually happens for phase transition with supercooling. That means like the phase transition takes a longer time and the temperature drops quickly at the later time. And here, this picture is the trapping process. So this gray line is a bubble wall, and on the left side is the true vacuum, and right side is the force vacuum. So the bubble is moving from left to the right, and the particles are originating on the right-hand side. They are massless on the right-hand side, and their typical momentum is the T, but it's much smaller than the mass of on the left side of bubble wall. That means when they hit a bubble wall, they'll be bounced back because the energy moment conservation. And the condition for them to penetrate is this theta function. The basic size of the momentum of the particle in the z direction should be larger than the mass shape. And this goes into the exponential suppression of the particle that can really goes into the true vacuum. So in this case, the dark sector is trapped.
So are you assuming a gamma is over 1 or something?
We assume like the fluid is moving with the bubble wall, in the wall rest frame. That's the most efficient case, and this will give the number I'm showing you this slide.
You do before some like thermal potential for phi, which is changing as the temperature drops.
Yeah.
But phi is no longer coupled to the standard model. Is it just getting this thermal potential from like self-interactions with other phi particles and with chi particles?
Phi and phi like within the dark sector, it trigger like a phase transition in the dark sector. Yes.
I think it's thermalized within itself.
Yes. Yeah. Dark sector is still strongly coupled. Yeah. So this is the flux of particles that can enter the true vacuum in the frame of bubble wall. And there are two velocity definitions here. Basically, the V wall here is what we usually talk about for phase transition. It's the velocity bubble, like in the global frame. And the quantity with that unit is what is the fluid, like the relative motion of the particles in front of the wall. So you can imagine if their relative motion of the local plasma with the bubble wall, there's a Lorentz boost, and they make it easier for particle to penetrate. but like it's also possible that there's no relative motion. Basically, like the fluid, local fluid is being pushed by the wall, and like they are moving together with almost no relative velocity. That's the case, you can get the highest trapping rate. So here, this the flux that can into the true vacuum is mostly controlled by this exponential suppression factor. If we assume V tilde is 0, so it is e to the minus m over t, which is the one we have seen in the last slide. And this float is a function of the trapping rate, which is the m over t. And you can see when we increase the mass shift of the particle in the true vacuum, the trapping rate almost goes to 1. So that means if we have the particle heavy enough in the true vacuum, we can almost trap all of them. And I will show in later slide that typically recycling needs phi to be like a 50 or 60 because we are dealing with super heavy dark matter. We really want to trap all of them in the force vacuum.
Why would V tilde be 0 or small? So you're saying V tilde is the relative motion between the wall and
yeah.
Like, why would that be small? Why would I expect the particles to be?
If the wall is like trapping all the particle and pushing the local fluid in some direction, and then the local fluid in front of the wall are like they get pushed by the wall, like they get a velocity because the wall is pushing them.
It's presumably consistent with the wall velocity being less than the speed of light, because like that's like the way you stop runaway is by having like significant interactions with the plasma outside the wall.
But like as I
velocity. So the wall is working through the heavy particles. The heavy particles stick to the wall, has take away a lot of the energy the wall was above it.
Yeah, I guess I understand the ones you've already hit can be moving along with the wall, but like as you hit new ones,
you have to carry it with you. So which actually, while you're expanding, you gain some energy from vacuum structure, and you lost a lot of the kinetic energy of the particles stacking, new particles stacking there.
Yeah.
So it's not saying like all the particles are moving in the same direction with the same velocity, but it's like the local bulk of the particles are moving with the same velocity as the bubble wall. But the inside the bulk particle is just still have like a similar distribution of their velocity, and like some of them are moving towards bubble wall, some of them in the other direction. Yeah.
Oh, but sorry, could I actually maybe you're gonna say this, but the 50 to 60 is that how, I mean, you wrote down a pretty simple like scalar potential. So is there anything odd that you have to do to get the 50 or 60?
50 to 60, I think is still okay. Like if you want like 100 to 100, that's a problem even with supercooling. Okay. That's the reason like set 60. So you cannot get very large because the supercooling has some subtlety to get that large value. And for the value smaller than 50, it's because we can almost get like 100% trapping, but because we have super heavy dark matter, even tiny amount of them goes into vacuum, we overproduce dark matter.
Oh, already at 50.
Yeah.
Already like it. Oh.
Yeah, because super heavy. Yeah.
Okay.
So if we have like a trapping mechanism to get almost all the dark matter into a force vacuum, then the evolution of force vacuum will be like the bubble was compressing all the particles and heat them up as a radiation. This is simulated by this group of authors for the black hole formation, and they found that the energy density of the dark sector inside the pocket goes with 1 over r to the force power. R over t is the radius of pocket at time t, and the force power is coming from like the particle are being heated up. So 3 of them are coming from the number density, and the power is coming from the energy they get from the bubble wall. So in this case, if we'll calculate what is the Schwarzschild radius of all the energy density inside the pocket, the Schwarzschild actually goes up because the dark sector gain energy. And so the Schwarzschild radius will become larger when the bubble wall is shrinking, and the bubble wall goes to a small radius. In the end, they will become the same value. This is the black hole formation mechanism. So at the time of the gravitational collapse, the radius of the pocket is equal to the Schwarzschild mass of all the energy inside. So in this way, we can calculate like during the compressed process when the black hole formation happens, and this gives us the final expression for the black hole mass. It's a function of the initial pocket size R star and the phase transition temperature T squared.
So just to be sure, so if you compress this region, then the particles inside this region will be heated up, right?
Yes,
so
yeah.
Have a large kind of energy. Still, this 50, 60 is kind of enough.
Like in that case, you need to like, I'll show later, like we are trying to put a cutoff that for the smaller radius size, because like that will generate PPH domination, and also for those smaller pockets, the dark sector are heated up more, and there's a chance they can leave the force vacuum. And you're right. So we need to avoid too much heating. Yeah. But this is not like a large, significant amount of heat change of temperature.
Okay.
Yeah.
I have a silly detailed question, and like you can totally ignore it. We can discuss later. But so like the trapping of these particles and like them being condensed, this is what's causing the black hole formation. So my silly question is, when I have like the first order phase transition happening everywhere or whatever, and I'm generating these interesting regions of still false vacuum, that's like some non-trivial geometry. So does that matter? I mean, I know you're assuming Schwarzschild and spherical symmetry and stuff like this, but I would imagine like in local regions when I like zoom in and see like what's happening as all these different walls are coming in, does like the non-spherical shape, would that give it some initial angular momentum?
So usually like this black formation is at like at the end of the force vacuum. So you actually assume the percolation of force vacuum, not the percolation of true vacuum. So in that case, usually I think the configuration of like the force vacuum is more spherical, but to my knowledge, I don't know if there's already a simulation to see what is angular momentum or like the shape of the force vacuum. So,
I mean, intuition tells us it's not really circle. It's not.
Yeah.
It's like it's weird.
but like they are overlap, then they will reshape itself like because surface tension. Again, like I think like my quick answer is surface tension.
Oh, sorry. Okay.
Yeah. Okay. Yeah. So what kind of pocket can form a black hole? This is an interesting simulation done by this group authors. So like if we have a pocket, they will collapse into a short radius and become black hole. But if you really think about this process, the phase transition is also going on. So there's a new true vacuum bubbles growing inside the force vacuum. So like you don't end up having a large black hole. It's possible that you have two separate black holes. So this group of authors, they did like a simulation of what is a successful collapse, assuming there's no new bubble sitting inside the pocket. And this tells us what's the distribution of the force vacuum pocket as a function of the radius. And this function is the most important part is here. So it's like exponential of the exponential here. This tells us like the PPH formation is very suppressed when beta or R star is large. So this is the cutoff here. When R star is large, that means if we have very large pocket, and we need more time for it to collapse, and it's more possibility to have a new force vacuum sitting inside. So we end up not having that black hole. And the beta value is inverse time scale for phase transition. Basically, beta larger means the rate of having new bubble inside the pocket is larger. So we also suppress the formation rate. So in the end, we will see that the black hole, the pocket distribution is look like this shape and suppressed at a large pocket radius. And the black hole formation kind of prefer a slow force of phase transition to make sure like a pocket can successful suppress.
This is exponential or exponential?
Yeah, it's very suppressed. Yeah.
How trustworthy is there?
I think it's still like the calculation is still like it's the best analytical calculation I have seen. I would say like it trying to do like inverse time projection. Assume we have collapse and doing it backwards. Assume there's no new bubble inside. Physics wise, it makes sense. But of course, if we have more like numerical simulations, they will give like more precise result on this.
Wait, if I get the true vacuum bubble inside a false vacuum bubble, are you still assuming the particles can't get inside the true vacuum? They're still stuck in the false vacuum?
Again, they push particles to like two separate regions. Yeah.
So like these two walls will come together and like I'll get particles forced into this like intermediate area. I would kind of expect this can still just form like multiple black holes or something.
Yeah, multiple black holes, but multiple smaller black holes.
Okay.
Yeah.
Okay.
Yes.
But that's still good.
It's still good, yeah, but like how to the matter of how to describe the formation, like how to calculate the numbers, but it's still possible.
Can I ask you a question about your dark matter model? Do the dark matter candy today have some charge or state?
The fermions are stable and there's no decay channel, so they're just stable dark matter candidate. The scalar
You
can
don't need to impose any charge.
yeah, no need to like assign a symmetry. Yeah.
So you don't have any symmetry.
Yes. So
You have asymmetric dark matter here, right? The chi bar and they cannot be both be there in this.
we can like Kagai bar. They just
now it brings to the five.
Phi is also heavy. Yeah. So here phi is also heavy, we assume. Like, but that depends on like how you do the model building of the phase transition. But it's possible that phi and chi are both heavy. In that case, the whole dark sector is trapped.
Do you have any relation between the chi mass and phi mass in your mind, or?
We didn't assume that, but does not like in the like.
Let's say they are of equal mass, right?
Mm-hmm.
So I still preferably to store my rest energy into the phis. Chi has too many degrees freedom.
Yes, and
so that affects your abundance calculation.
let me.
Right, okay. So,
Yeah, like for the basil, we assume like they have equal mass, mainly because of kinematics. Yeah.
But if they are of equal mass, right? So any pair of chi's will more preferably come into phis.
Yeah, but like inverse process is also happening when they are like in equilibrium. Yeah. Yes.
Yeah, but eventually it's dominated by the rest mass of this particles.
The rest mass is like tree level rest mass are zero in the true like in the pocket. So like they require some thermal mass. Yeah.
Are you assuming that phi particles are also going to be squeezed by these?
Yeah.
Okay.
Assume like whole dark sector. Yeah, but as Jen said, if like chi annual to phi and phi has a much smaller mass, then phi can go to the true vacuum and leak energy. So this is what has been started in the previous group, and they need to like assume some certain formation mechanism. Yeah, but if you can compress, assume like they have equal mass, then it's much easier to form black hole. Yeah.
Then why do you need a chi at all? Right? Why do you claim I have a chi that who during after phase transition get a much heavier mass? I will squeeze.
Oh, you mean like phi if we have a dark sector or phi alone?
Yeah.
Like I think you cannot have first order phase transition with only one scalar.
Yeah, sure.
Yeah.
But apart from that, do you have any reason to introduce chi? Why don't you call phi your dark matter particle?
In principle, you can. So generally, if you do a model building of dark sector into black hole and reproduce dark sector, if you have like a different dark matter candidate or only phi, it's possible. Yeah, but here it's just a working model to show how it works. Yeah.
There's an intuitive inconsistency there, right? You require the phi sector to get a huge web, right, which later on transport to a huge mass of the particles in those sectors. That forbids them to do this phase transition.
Yeah. So that's you're right. So they require like the assumption of the black hole formation of the dark sector requires like the huge mass increase. Yes.
But the huge mass increase is induced by this phi sector. Whose phase transition happens at a temperature T that generally is comparable to the other scales in this.
Yeah, so that's the place you need to introduce some supercooling and like at the percolation time of the force vacuum, like the temperature drops more quickly than you usually assume for standard first order phase transition. So I may need to like go quick on this part, but so in general, once we have the distribution of force vacuum pockets, each pocket will collapse into a black hole. And if we assume all the pockets can successfully collapse, there's a problem because all the dark sector in the in the early universe will be collapsed into a black hole, and usually they will all overproduce the primordial black holes. Then universe will enter a PBH dominated era. The PBH dominated era is like a matter dominated era, but the PBH will evaporate equally to dark sector and small model sector, and you can compare how many energy density will go to the dark sector, and it's only a matter of like a ratio of degree of freedom that usually overproduce the dark matter. And for that reason, you need to make dark matter super light, and it is contradictory to the assumption here. So preferably, we want a black hole formation only at the peak of the pocket distribution, and we don't want a PBH formation here. And the way to do that is to suppress PBH formation by introducing energy loss into STEM model. So for this reason, we can assume there's a dark sector STEM model interaction with this operator, and we can calculate what is the annihilation rate of a dark sector into the STEM model. The annihilation is suppressed by the scale, a very heavy scale lambda. So the annihilation cross section is basically alpha square over lambda square. So the annihilation is only effective when the temperature of the pocket is high, which is happening for smaller pockets. So in this case, we can calculate what is the annihilation rate times the time we need for the collapse to be smaller than 1. This tells us the initial pocket size should be some larger than some fraction of the initial Hubble radius times some scaling of the parameter that is from the portal coupling. Basically, it tells for the smaller pocket, they have to compress more, and the temperature is increased more compared to the temperature of FOPT, and the annihilation into STEM model is more active, and the energy is lost into the STEM model that goes through true vacuum. So we don't have enough dense region in small pockets, and this leads us to the PBH mass function in this plot. So if there's no energy loss channel, the PBH mass function will follow this black line. So it's a very extended mass function, and it has a lot of light PBHs. But if we introduce the energy loss channel, we can put a cut on the PBH mass distribution, and we only get the PBH mass function as the shaded color region, which is sitting on the peak. And this is this PBH mass function now gets controlled by the interaction between the dark sector and the STEM model sector with a very high EFT like scale lambda. And this is PBH mass function with a theta function controlling the shape. And if we assume the PBH distribution is the delta function, we can start to calculate how many dark matter particles we can have. So this is a calculation of Hawking radiation. We assume the particle production follows the black body spectrum, and then we can integrate the number of particles get produced throughout the lifetime black hole. So this is the number of particles that can be produced. So n total, if we assume a fermionic particle chi, then n total is the total number of chi particles can be produced per black hole. And if the initial temperature of the black hole is larger than the mass of chi, you can imagine the mass of chi is almost 0 compared to the black hole Hawking temperature. So the amount of particle can be produced is independent of the mass of particle. It only depends on the degree of freedom of the chi particle over the total number of degree of freedom that can be produced by a black hole. So the number of chi is proportional to mass of black hole square over n Planck square. It's like the black hole mass is equally distributed all the mass degree of freedom. But if the particle is heavy, as in our recycled dark matter case, the particle production rate is suppressed by the 1 over m square of the dark matter mass. And if we know the number of dark matter particles can be produced per black hole, then the yield of dark matter is just the number of particles produced per black hole times the number density of black hole. And this n chi is calculated in the last slide, and the MPBH is the formation rate, how many black holes are formed at the initial formation time. And we can put the dark matter yield into the this equation to match the radial abundance of black hole dark matter today, and this tells us what is the required PBH abundance at the formation time. So this beta PBH is the fraction of energy density collecting the black hole versus energy density of radiation at the formation time. Usually this number is very small, and this is controlled by the 1 over m chi and 1 over n chi of the particle model side, and the MPBH versus the TI of the PBH formation side. So basically it tells if the particle is heavy, then this thing is gets suppressed. And if we can calculate what is the beta PBH by the pocket distribution after we put in the card, and this all goes if we take this distribution of PBH from the color shaded region, this gives to the parameter space on the right hand side. Let me explain this. So the y-axis is what is the beta of H star of the first order phase transition we need. The controls like how fast the phase transition happening and how many pockets can collect into a black hole. And you can see because the pocket distribution has that double exponential expression, in the end, everything is mildly dependent on the beta PBH, beta of the phase transition, and different values, the different colors at different phase transition temperatures. And on the horizontal axis is what is the dark matter mass as a function over the phase transition temperature. On the left-hand side, the shaded region means the PBH, the dark matter mass is too small to get all trapped into first vacuum. So the dark matter enters through vacuum, become like an overproduction of the dark matter radial abundance, so they get excluded. The parameter space should live on the right-hand side, and the very right-hand side is controlled by how you model the phase transition to get VAV over T. And the preferred region is like somewhere at 60 to 65. So you don't require very strong supercooling. And this is like the last result plot of the recycled dark matter parameter space. It's a function of PBH mass and as a function of dark sector mass. So PBH mass of higher than 10 to 9 gram excluded by BBN. PBH mass lighter than 0.1 gram is consumed by CMB. So the recycled dark matter is kind of living within the narrow band between the two solid lines, assuming different R star or H star of the initial pocket size. To the left-hand side of this solid band, the dark matter mass is too small, so we overproduce them at the trapping process. To right-hand side, it's because the value of T is too large. It needs some extra model building for the phase transition side. But like within these two bands, you can get a model of dark matter produced from the recycling mechanism. And the dashed curve are the beta PBH value we need to produce the correct radial abundance. And you can see they are very small value because PBH redshift as matter. So like even if they are produced at a very small amount, they become more and more dominant over the radiation. And when they produce super heavy dark matter, we can actually get the correct radial abundance with very, very small amounts of PBH initial abundance at the phase transition. And you may ask, like, if this formation mechanism produce everything with the correct radial abundance, how to test this? So I think this is a general question about if we have light PBH evaporate before BVN, how do we know they ever exist? So the Hawking radiation coming from the evaporation of the PBH are thermalized. So all the information of their existence are lost. So we need to get some decoupled like information from the early time. And here are different possibilities. We can have right-hand neutrinos or dark radiation, but like we may be able to constrain with an effective or other things, but to directly detect them is difficult. And the gravitational wave coming from the Hawking radiation is usually peaked at like the Hawking temperature. So they are very, very high frequency gravitational wave that is also difficult to probe. And another possibility is that we have the formation mechanism that is generate some very large density contrast. For example, the curvature perturbation will solve second order gravitational wave, and the first order phase transition will also generate gravitational wave like with bubble collision or with like a sound wave. Those gravitational wave, if because the PBH formation is always at a very high temperature, the gravitational wave produced from the formation mechanism is also at high frequency, but they're not very high. Typically, they will be at megahertz to gigahertz. So if primordial black holes ever exist in the early universe, this formation mechanism will predict a high frequency gravitational wave for the future search. And here we are plotting the benchmark for like a gravitational wave signal from PBH solving the dark matter rack abundance. And in the future, if we have some new tabletop experiments look for high frequency gravitational wave, then it's possible we can test this possibility. I think I'm very over time, so how much time do I have?
Good. Another 10 minutes.
Okay, I think I can wrap up in 10 minutes. Yeah. So this is the PBH mass between 10 to 9, 10 to 15 grams. So I would just emphasize they are actually very constrained by BB and ZMB because black holes are evaporating at that time, and they will have precise measurements. And if a black hole is heavier than 10 to 15 grams, it becomes stable and it becomes dark matter candidate. So this is the parameter space we are looking at in the next 10 minutes. So these black holes, they are light. Their gravitational interaction cannot be tested by the current astrophysics measurements. The effect we can look at with their gravitational interaction, we can look at as low as 10 to 22 grams from gravitational lensing, but below that, dark matter can make up 100%. Primordial black hole can make up 100% dark matter within this window. But if we keep decreasing the PBH mass, their Hawking radiation become more efficient, and they are producing particles, and we are looking at them and setting a constraint on their abundance as they are decaying dark matter.
But future gravitational lensing will close the window.
I'm not sure, but for the current projection plot, I see this window is not closed. Yeah.
Well, but they're very low mass, so they're not going to be very much.
Yeah. So the asteroid-mass primordial black holes are evaporating at MeV energy. So we can produce photons at MeV energy for galactic and actual galactic search, or their energy injection during CMB or 21 centimeter signal. MeV is also higher than reservoir electron, so we can produce electron positron with black holes around us today, and look at energy injection or annihilation of like 511 keV line signal, or they can even produce neutrinos, and we can look at them with super chemical. So I would focus on the gamma research because this is currently the best spectral measurement we can have. So the total number of photons coming from primordial black hole is from the primary photon, that's the photon directly produced, or second photons, which is coming from secondary radiation, final state radiation of charged particle or the pion decay. So this is a photon spectrum from a primordial black hole. You can see most of the photons are dominated by this dashed green line, which is the primary photon. And because the MeV energy is still not enough to produce enough pions, the pion contribution is small. And for the final state radiation of charged particle, it become a tail of low energy photons, but with a very fixed spectrum. So when we are looking at the primordial black holes with the gamma spectrum, we mainly look at this primary photon peak. This is a projection of future experiments and the constraint from existing data. If we assume primordial black holes are dark matter in the galactic center, we can look at the galactic center and see if there are additional photons produced than we expected. Using COMTEL data, we can put a constraint on primordial black hole with mass lighter than 10 to 17 grams. They cannot make 100% dark matter because if they are light, their radiation power is very much higher because of Stefan Boltzmann law, and they can be only fraction of dark matter. But in the future, our MeV indirect detection search will be able to put a much better constraint and cover a PBH mass range of 10 to 18 grams. So this solid color curves are future constraint projection, but they can also tell us if we may have a good sensitivity to something coming from black hole. And the future possible experiments are AMIGO, ES-Shogun, and APT. They are actually different kind of proposals. So basically, the future MV sky will be covered by experiments with much better sensitivity than COMTEL. I think like they will cover the gap between X-ray and the GeV sky, and this, if we can cover the energy range of 0.1 MeV to 100 MeV, this actually corresponds to a PBH mass of 10 to 14 to 10 to 17 grams. So future MEV sky experiments are ideal for looking for primordial black holes of asteroid mass.
These spectra, gamma ray spectra, assumes that black holes are only produced at one mass, or is there like?
They assume one mass when we do the projection, but like they are also constrained if we assume like a log normal distribution or different kind of distributions. But the way we set the bound, but it's counting photons, they are still the same. Yeah. And also, if we can have observation of Hawking radiation of photons and gravitational wave coming from the formation mechanism, both of the signals will be very strong in the future. And we can actually do a spectrum fit to the curvature perturbation and produce primordial black holes. Here I'm showing a fit of LISA, which is shown in the blue band, and the ES-Shogun as the green band. So you can see they have an anti-correlation. And if we have multi-messenger search for the primordial black holes, we can actually fit in the formation mechanism of the primordial black hole with different kind of signals. And
ES-Shogun is some kind of satellite gamma ray detector.
Yes, they are looking at the Hawking radiation, and LISA are looking at the gravitational coming from the formation mechanism. Yeah, and we can fit it both of them. Yeah, BBO doing a very good job. Yeah, yeah.
P zeta can be anything.
P zeta has to.
Anything at the scale. You don't have any.
Yeah, this is like assumption of the shape.
Why did you choose this point?
I think it's usually assumed.
People assume that, but there's no any reason to choose. You can choose anything.
I need to think about, but I think for our study, we assume like it's just a model that people usually use, but I need to think about
this fits only works for that choice.
Not only for this, like the gravitational wave.
It's like it's not difficult to make such a fit because you have huge freedom of choosing P zeta. You don't have any constraint with P zeta for such a simple.
Yeah, if you can have random shape, it's possible. Like yeah.
You can fit anything.
Yes.
For instance, in the ultra-solar inversion that you mentioned, can you actually compute this function for originate, how it densely carry and say like in the assumptions?
Yeah, if you starting from like an inflation model and calculate the curvature perturbation, you can give like shape and that's a fit like the model from inflation model to the gravitational wave spectrum. But like here, if you don't know the model, but you do it backwards from gravitational wave, yeah, that you need to make something. Yeah, I think there's some reason, but I cannot remember it now. I will check it and get back to you.
You don't need any inflation model. You can assume this. You can do that, but you can choose also other one.
Yes.
Simply because you can.
Yeah.
Well, I'm just asking, what's the meaning of showing? Sorry, the working of this fitting based on the choice of the some specific function.
I think here we really want to emphasize that we can have multi-messenger search to like fit the curvature perturbation in different ways, and the precision is good enough to like. Usually they have like different orientations and they'll be able to fix the true model of formation mechanism. And this becomes like you can not only discover PBH, but you can measure the formation mechanism and their abundance with some better precision. Yeah. And like the main point of looking for a better precision of PBH measurement is that if we know the PBH producing standard model particle, they're also producing like new particles beyond standard model particle, like the axion like a particle. The only thing we need is that the particle mass is smaller than the Hawking temperature. That means asteroid mass PBH can produce MEV standard model beyond standard model particles. and the degree of freedom of this beyond standard model particle should exist in the spectrum. So in that sense, primordial black hole is like a particle factory with gravitational production mechanism in the sky. And if we can measure Hawking radiation spectrum precisely, we can see if there are new particles produced together with standard model particles. An example is the axion-like particle produced by a primordial black hole and decay to 2 photons. And for that, we can just add the decay of axion-like particle into the total gamma ray spectrum. And let me show you what the spectrum looks like. If there's only standard model, the spectrum looks like the purple curve. But if there's also axion-like particle getting produced by the primordial black hole, they decay to photons, they will generate as like a double peak feature on the left side of the primary photon. And since the production is gravitational, if you assume we do have primordial black hole, anything like in the particle spectrum should have been produced. So you are measuring one spectrum, but you should be able to read out what like all the particles that being produced with this gravitational production mechanism. So what we are proposing is that in the future, if we have some precision to measure Hawking radiation spectrum better, we should be able to do a spectral analysis to see if there are indeed axion-like particle produced.
And the blue line there is essentially QCD axion.
It's a very, very light axion. Yeah, but yeah. And
we need to assume that conversion to photon is 100%.
yes.
You said they have different conversion rate and different conversion spectrum. You will make sure you will lose your prediction.
You will need the new particle you introduce to decay to something you can observe, and then you can compare a spectrum. And I will show the axion pyramid space in a few slides, and you will see it's a decay length that's constrained there. So we propose to look at the galaxy center with primordial black holes and produce primary photon, final state radiation, and axion decay. And to calculate the flux from the primordial black hole at the galaxy center, basically they behave as the decaying dark matter in the galaxy center, and we can calculate the flux in the standard way. We do the indirect detection search. And this is the real spectrum we'll see from a galaxy center search. And the main thing is the dashed line is the future E estrogen sensitivity. And if the color curve sitting above this dashed black curve, that means we have enough photons that enter our beams, and we can do a spectral analysis. And we perform a fit of the model. So basically, the left-hand side is if we keep increasing the number of photons enter our detector, we go and if we assume the true model is particle spectrum with axion-like particle, then from the photon spectrum we can fit through a true model and see there's indeed axion-like particle getting produced. But for the fourth model that we assume standard model spectrum, the spectrum never fits through a true model. So this is kind of a spectrum fitting from the gamma ray sky. And if we do the projection to the pyramid space of primordial black holes, this is the way we usually put constraint on FPVH versus MPBH. So the region shaded in gray color are the excluded region. And in the future, if we have ES1, we can see primordial black holes above the dashed color curve. And the solid color curve is above the dashed color curve. It means if we have slightly more amount of primordial black holes, we get enough photons to fit the gamma ray spectrum. And for any allowed pyramid space above the solid color curve, that means we are able to distinguish a standard model serial assumption versus the axion-like particle serial assumption. So here is a region that we can identify the existence of axion-like particle with the Hawking radiation spectrum of the primordial black hole.
What's the decay constant here that you see?
This is assume the 100% decay rate. And I will show you in the next slide on axion pyramid. Sorry. So it's in this slide. So if we assume the axion decay rate is controlled by the GI gamma company, this pyramid space we can prove by the by looking at the gamma spectrum of primordial black hole. So basically, different color regions are coming from different assumptions of PBH mass. For the lightest PBH mass, we can cover a higher axion-like particle mass. And the edge on the right-hand side is that axion getting be heavier than the Hawking temperature, so their production is exponentially suppressed. And the lower edge is coming from the decay length. We are looking at the axion decay from galaxy center because we really want to measure the instantaneous Hawking radiation spectrum. So for the pyramid space below this, so the axion become long-lived, so they do not decay before they reach our detector. But the color shaded region, we almost have like all the axions decay, and we will be able to measure spectrum. And they kind of overlap with some uncovered region from collider experiments, or like cosmological triangle, or very small coupling region that cannot be probed so far.
So you can't probe QCD axis.
QCD axion too long-lived, yeah. Maybe some conversion mechanism, but we haven't studied for galaxy center, yeah.
And I don't know how many more slides on you have, but if the black holes, if the PDHs form all the dark matter, you don't have a dark matter motivation for ALP. So I know that they can exist, so there's sort of like them, but they don't even solve the strong secret. So what I'm saying is you're invoking two magic fairies to solve the dark matter problem.
So here the axion-like particle is not dark matter. So we're saying like the dark sector particle in the spectrum, and like any dark sector particle in the spectrum should have been produced by the primordial black hole. And here is like a search of looking at the Hawking radiation spectrum to see if there are any dark sector particle getting produced. And the axion-like particle, which can decay to photon, is an example.
Okay.
Yeah. Yeah, so like the main idea is that if we do observe a Hawking radiation spectrum in the future, there's a lot of information contained in the Hawking radiation spectrum. Yeah, so you kind of measure one spectrum and you can put a constraint if it like perfectly agree with the standard model assumption.
To be able to extract a very precise spectrum in the galaxy center, which is very noisy environment.
Depends on like how many black holes we can have. Yeah,
in terms of gamma rays.
Yeah, like I agree. Like there are certain data like spectral analysis to do. Like with photon is one example, or like if we can do with positrons, like with 511 like a line spectrum. Neutrino is a bit difficult to look for. Like there are certain like constraint from superconductor, but it's weaker than directly looking at the photons. Yeah, so
hard to detect those.
Yeah. Yes. Yeah. Since I'm very over time, I will skip the super radiance part, but let me go to the summary here. So basically, like, we have different possibilities from black hole mass, and for like black holes in our universe, they can do dark matter production or baryogenesis, and there's a chance to look for high frequency gravitational wave for their existence. For asteroid-mass black holes, they can be dark matter. So like we can using indirect detection search to see if they may have a few like a fraction of dark matter, and because they are evaporating at MeV energy, we can also look for MeV dark sector models with like a fit in the spectrum. Yeah, thank you.
Cool. So you put grade 45 to mine. Well, it doesn't depend on my answer.
For the gamma research, we do calculate the gray body factor. It depends on energy. So if the energy is much higher, it's a geometric optic limit, but for low energy, it gets suppressed. So yeah.
Could you remind me how large is it? Like in third is it like over one, or like 0.9 or something, or smaller?
I think it's with like a order maybe a factor of 5 or 10 larger than the Hawking temperature. I think it's almost a constant. Let me see if I have back slide. Sorry, I don't have that, but I can check that and get back to you. But I think for the high energy part, it's almost a constant, and I think all the one fraction. Yeah.
Yeah, I was just wondering, like a gravity bucket is like, kind of scattered by gravitational potential, and again, absorbed by the black hole.
Yeah.
Including the plasma phases, and in principle, and this process, we can also emit some like photons, like negative charged particles. So we can emit some photons by joints or something. The structure of the motion in this particle is unchanging, but probably that kind of effect is too small.
I haven't think about this because usually gravity factor are calculated for like a observer at infinity, right? So
yeah, but in principle, I can imagine that so this particle is nature, but then kind of reflected by the gravitational potential, but in between these two parts, like it can use some particles, and that in principle will contribute to a secondary like a spectrum. So maybe like excuse me, so that you don't have to generate. I was wondering whether that gives you some effect on this, because you are using the spectral sharing sense.
Yeah, at least in this analysis, like we always assume like a particle can go like as a free particle that goes to infinity. So we haven't included this effect, but I'm not sure like how strong it will be. Yeah.
So could you just briefly summarize the super radiance effect then?
Okay. Yeah. Yes. Sorry. So the super radiance effect says like we can produce, if we have a spinning black hole, we can use like a rotational angle of black hole to produce particle. So basically like a scalar particle can have a huge occupation number on a black hole, so it can get scattering a few times and generate a huge cloud. And if we look at the super radiance, we need to calculate what is the imaginary part of the omega of the cloud, and the particle can grow exponentially. Basically, for asteroid-mass black holes, here's the super radiance that can happen between CMB and today. And for asteroid-mass, the size of short radius of the size of black hole matches to like the wavelength of KeV axions. So we can use, if there are a KeV axion exists, then we can produce them with a super radiance of black hole. Basically, the idea is if we start spinning black hole at the early universe, we wait for some time, then super radiance instability comes up, and there's a cloud can be produced as the red curve, and the black hole will lose its spin. And since we are measuring primordial black hole with a Hawking radiation, and the Hawking radiation depends on spin of black hole, once the black hole lost its spin, the Hawking instantaneous spectrum changes from the blue one to the orange one. So when the black hole spin down, the Hawking radiation power decrease. So the way we put constraint on primordial black hole or curved primordial black hole depends on the spin assumption. So if a super radiance ever happened, the constraint on curved black hole abundance will become weaker. And more interesting that if we look at actual galactic spectrum, which is the Hawking radiation spectrum that gets redshifted in time, we look at the spectrum to lower energy. So we're tracking the black hole spin at higher redshift. And if a super radiance happens, we will see a black hole, the actual galactic spectrum for coming from a rotating black hole to a non-rotating black hole. So there should be some transition in the actual galactic spectrum telling us super radiance ever happened. So this is one way to measure the super radiance of actual, like with actual galactic Hawking radiation flux. It's also possible that the super radiance cloud will decay to KeV photon lengths. So in that case, if we have curved black hole at asteroid mass, if we have KeV axions, there will be correlation between central Hawking radiation, actual galactic Hawking radiation, and KeV line search. So it will tell us a lot of information about KeV axions. Yeah, everything comes from this, like super radiance happening between CMB.
Black hole reading we measure spectrum. I mean the spectral information from black holes. Energy of the module.
Yeah, the light one. Yeah. The Hawking radiation is like a spin measurement in that sense. Yeah.
Let's send how good.
Thank you.